Recall from last time. So what we did is we defined the space of bounded variations. So it is a set of functions from A, B to R, for which the total variation is less than infinity. And since the variation of C times F is equal to absolute value of C times the variation of F, and we also know that the variation of a sum of two functions is always less than or equal to the sum of the variations. So that happens whenever F and G belong to the BV space, the BV set. And I mean, my point is that that makes BV a vector space. So then next we also managed to define a norm. So this norm satisfies it's bigger than the sup norm. So in other words, convergence in bounded variation is stronger than uniform convergence. Huh?
You said you will give this on the exam.
No, I proved it.
Oh, you did.
I did. I want to just we'll do a little true or false, and then we continue to develop this theory a little bit. Also, BV is a complete vector space, so it is Banach. It's a Banach space under this norm. So in other words, it's complete. Okay. So what else did we observe? So 3. For each function in the space of bounded variations. We defined the function v of x to be the variation from a to x of f. And we saw that a, v, and v minus f are increasing. B, we have that f is equal to v minus f. So that implies that any function in BV is a difference of two increasing function. So it's the difference of two increasing functions. And C, V is right or left, continuous at x if and only if f is right, left, continuous at x. Okay, so that's what we observed. So let's just do some comprehension checks, so maybe it's a little more fun. So it's true, false, and justifications, of course. True or false? If Fn goes to F pointwise, then the variation of Fn goes to the variation of F. And I don't remember, I might have mentioned that last lecture, and I might have told you something wrong, perhaps, right? So think about it, and just let's say for how long do you need to think about it? So roughly speaking, what you're imagining is variation is just a generalization of arc length. And actually, in this case, it's an arc length in one dimension. Right? The reason it's not just arc length is because, well, first of all, the way we're dealing with it, it's specialized to one dimension. Secondly, it's able to deal with non-continuous functions. Right? Arc length requires actually differentiable functions. And this one is therefore able to deal with even not non-continuous functions, right? And what's the point of all of it? Actually, very deep, very far. I barely see it myself. I mean, if you open books on quantum mechanics, it's full of that stuff, right? It's full of functional analysis, and this is what functional analysis roughly looks like. That's just part of it, right? So you have rich representation theorem, which you might be familiar with in linear algebra with some version of it in finite dimensions. Okay. Right. So is this true or false?
False.
False. A few people say false. Well, you see, you're much smarter than me because in my notes last night I wrote true, but I was wrong. Right? It is false.
I have a counterexample.
You have a counterexample.
Yeah.
Good.
It would be the characteristic function on like a closed interval. You can create like fn being the characteristic function defined on like a finite enumeration of the rationals.
Right.
And that would have bounded variation for all fn.
If it's finite, yes. Yes.
But then it converges pointwise to the actual characteristic function of the rationals, which is infinite variation.
So what you do is you lift points, something like this, right? So that it converges pointwise. Be careful because remember the what is it? Was it Baer-Osgood theorem and whatnot? The set of discontinuities on the characteristic function Q, if that's what you mean, right?
Yeah.
It's everything. It's dense, right? But the set of discontinuities of a limit of continuous functions is always nowhere dense, right? So it would not quite be pointwise. You're lifting point by point, but I guess if maybe I'm hijacking your example, maybe I am, right? You're not dealing.
You define like the finite enumeration of irrationals for fn to be 1, and then the rest of AB to be 0.
So you're just dropping, so non-continuous functions, I see.
Yeah,
no, so I did hijack your example. I thought about continuous functions. So your counterexample is right. So let's put it false. Counterexample A. A, yes, because we're not dealing with continuous functions, so what I said does not apply. Counterexample A. So let's say, let me see how can I write it. It's cool. So, so what we're going to say that f of x is equal to 0 if x is an irrational number on, let's say, on AB, right? So I'm not going to write it, but on AB, and 1 if x is a rational number, correct? And then what we do is we are going to enumerate by xn. That's just an enumeration of Q. Okay? And then what we are going to define is fn of x to be equal to 0 if x is not x1 through xn. X doesn't belong there. And 1 if x is equal to xk, where k is 1 through n, right?
Yes, it's not n, right?
Yeah, 0 if x is not.
0 if x is not, right? And 1, so the idea is what we are doing is we are taking, this is the first step, so we are lifting a point, and then next step we are lifting 2 points, right? Next step we are lifting a few more points. And sequentially, we are going to lift off rational numbers, right? Right. So this function is not continuous. So what I mentioned about Osgood does not apply. And pointwise, we can say Fn goes to F pointwise. But one second. Is it a counterexample? So what's going to be the variation of AB of Fn? It's going to be, what is it? It's going to be 2 times n, right? 2 times n. So for each n, right? It's going to be 2 times n. And this is going to infinity. But what about the variation of f? That's also infinity, no?
Yeah.
So is it a counterexample? They both go to infinity.
Oh, yeah, I guess it's not.
Oh, sorry. So you see, so this one.
Oh, I see. I felt like, well,
Also.
usually Fn was bounded, but I guess that's a...
Right. So this is not
No.
counterexample. Not. You see.
Yeah, I see that now.
Oh, you see, but yes, good. Sorry, I was sucked into the believing that this is a counterexample, but. So this definitely pushes out. I mean, it's not pointwise, not closed under bound variation. Those are bounded variation, yet this is not, right? All right, so let's see. This, you remember, I'm erasing it, right? Well, I think I have, hopefully I'm not wrong myself, right? I only sketched it as a last line, but I think I can show you a counterexample and one that also uses continuous functions, okay? So maybe you'll find so here counter example me neither, I don't know.
I mean, are you talking about?
Although that's more interesting, I think. So counterexample A, what I thought is, let's say Fn, I'm going to draw it because writing an explicit formula for it is a little annoying. So let's say this is 1. And this is 0, so somewhere in between there is the point 1 over 2n, and here is 1 over n. And not drawn really to scale, but here is elevation n. So Fn is going to be this function that you remember from pointwise convergence. Okay? From pointwise convergence, so that's what our Fn is. So then Fn Fn goes to the function f, which is equal to what? Pointwise. What does it go pointwise? 0. Right? So what you see is the pix 0. But variation of AB of Fn is equal to what? What's the variation here? Notice you don't look at the graph, you just look at the projection of the graph onto the y-axis. So what's the variation here? 2n, right? It's this piece and that piece, so it's 2n. So variation here is 2n, which grows to infinity, whereas the variation of ABF is simply 0. Because this is just a constant 0. Okay, so that's 1. So let's now change this. By the way, if P is any partition of the interval AB, then and we know that Fn goes to F pointwise. That's why it's very tempting to say, at least it was tempting for me to say yes. I didn't think about it more. Fn goes to pointwise. So what you have is limit as n goes to infinity of V Fn P. That's just limit as n goes to infinity of some sum of the form k equal 1 to some m of f tk minus f tk minus 1. Right? Oh, there is an n here. And this limit is equal to the summation ftk minus f tk minus 1, which is the variation of f over p. So it's tempting to say that, you see, because for any partition this holds, it's tempting to say that the answer is yes. But there is subtlety here. You see that, right? So for any variation, so you might think of this as an approximation of the variation of f, right? Now for any approximation you pick, you have pointwise limit is enough, because you just don't need to bring the limit over finitely many nodes. So it's just a limit of a finite sum. It's the sum of the limits. Okay. Now let's see if we can see then if we strengthen this. So true or false? Yeah, uniform convergence, right? Natural. If we have uniform convergence, then variation is it true now? See, this is pointwise but not uniform. What about if I force uniform convergence? Is it going to help us?
Sorry, Professor, just before you go there.
Right.
So for this one, does that mean just like if the total variation is bounded, this will always be true? Like since I guess the only way these two proof are different, it's just like the total variation of the.
I mean, I pushed it to infinity, right? So you can see that this the sequence actually goes to infinity. That does not have to happen. Actually.
Yes. So just, I mean, like if this is bounded, like if you can reach the supreme rather than like if the maximum.
Well, so that's actually the content of the next example. If it's uniformly bounded, that if there is a limit, it's going to be uniformly bounded, right? So what do you think? So one person says yes, uniform convergence does it, right? Uniform convergence means that the graphs of both, so the graph of the sequence of functions starts looking like the graph of the limit function, right? So would it force bounded variation? Sorry, would it force more than that? Will it force convergence and variation? Yes? Who says yes? A lot of you, right? And if my counterexample is correct, you're wrong. And then I can tell you why. I mean, how you can think of it, right? So again, the way to think about bounded variation, think about a particle moving in a straight line, right? So instead of the graph is just like a two-dimensional stretching of actually something that happens in one dimension. What happens in this graph is that it's stationary and then goes up and down like this, right? So it goes up and down, goes up and down. That's really what this means, right? It just with each sequence, the particle moves higher up. That's what happens here, right? So in order to create, so what is uniform convergence doing? Uniform convergence is it's like a press, right? It's pressing those particles together, right? So the particle has less room to bounce, right? So how is it going to create more variation? By bouncing faster and faster, like this. So basically, variation is by moving up and down, right? That's what controls variation, right? So you need to create an example so that when you squish things together, the bouncing is just going to compensate. It's going to be faster and faster. So here is the example I thought about. Wow, wonderful, right? The same, honestly, it sounds like exactly the same example, right? I guess I mean, if you think about bouncing, right? So here is, the answer is false. False. And the reason is you can just take the function fn from 0, 1, let's say, to r, and we have fn of x. Probably you are thinking about the same function, 1 over n sine of 2 pi nx, right? So this is this is basically, it's a press that's squishing this function to 0. So if you forget about the graph is like this, but if you just think about one-dimensional, what's happening in one dimension, it controls the particle, it's moving up and down, right? So this controls frequency, so the frequency is increasing. But then the amount of jumps up and down are, so it's like this, right? So then let's calculate, so we have that fn converges uniformly to what function? To 0, exactly, right? It's forced to converge to 0. Yet variation of 0, 1 fn. Can you calculate what's the variation of this function? What's the variation for 1 over n sine of 2 pi nx? No, I mean it's not infinity, right? Remember the way you can do it is, remember that variation is very easy to calculate for increasing and decreasing functions. Now sine is just built of how many increasing, how many decreasing functions. Two increasing, two decreasing, right? So we have the altitude that's going to be, it's going to be 1 over, yes, wonderful, very good. So it's 1 over n times 4, which is always 4, right? So the variation is always 4. And I'm going to draw a picture for sine so you understand why variation is always 4. And variation of f is simply 0. It's flat, right? Now, how did I calculate the variation of fn to be 4? Well, consider the graph of sine. Okay, the graph of sine. And then I break it into, you see, this is just a two-dimensional projection. I'm really only concerned with one dimensions here, right? So what is this? This is really This is 1, right? So up to here it's 1. Then this is another 1. Right? That's because I broke it down the middle. There is increase. It's 1 up, then it's 1 down. Right? But in variation, you measure the size of you measure not the displacement, but the distance traveled by the particle. So it travels 1 up, then it travels 1 down. Then it travels 1 up and 1 down, right? So here it travels 1 down, right? Sorry. First 1 down, and then finally 1 up. So altogether is variation is 4, right? Now, if I increase the frequency, then in this interval between 0 and 1, I have n copies, right? So it's n times 4. And instead of jumping all the way up to 1, they now jump all the way to just 1 over n. So the variation is just 4. Okay? Good?
Sorry, because we still back to that proof.
Right.
So how this proof differ from the Cantor example again? Sorry.
This is not a proof. This is just saying that over any fixed partition, then the convergence is gonna happen if you have pointwise convergence, right? So for any fixed partition, if you're trying to estimate a bounded variation by finitely many nodes,
Yes.
This is gonna be true.
So I feel like this proves the counter of that.
Yes, that's what I felt, and I might have actually even said last lesson that this is true. I might have said something incorrectly. This is not the counter, and it's a little subtle. What happens here? Notice that as you move, how should I say what happens here really? You see, this is some approximation to the variation of Fn. This is the approximation to the variation of F. Now, as soon as you switch n, you need a different approximation. You need a different partition. That's really one thing that happens, you see? You see, I mean, if you think about it, right? So let's say you approximate, you pick a partition P that is a good approximation for F. So it's a good approximation for variation of F. So pick a partition for which this is almost the same as the total variation. Make sense?
Wait, so equation sign doesn't always hold? Or, I mean, like whether the equation is true.
So this equation is true.
Yeah, okay.
It's true.
Okay.
But this equation does not imply that you have convergence in variation.
Oh, gotcha.
You see what I'm saying? This implies that if you have and here is what happens. Again, it's a little subtle. You see, what do you do when you think of variation? You think of approximating the variation by something like this. Take a p, approximate the variation of f. Make sense? So for this p, this is pretty much the variation of f. This is almost the same as the total variation, almost the same as this thing. Right? Now, if I refine this partition, I can also make it almost the same as the variation of fn. But the thing is, when I push the limit, I change fn. So as I change fn, I have it now f sub k, or whatever, f sub j. For this new f, this might no longer be a good approximation. This partition might not work. That's really what's happening. Do you see roughly what I'm talking about? So this, I can pick a partition that for a fixed n, is a good approximation to the total variation of f sub n, and a good approximation for the variation of f. But when I push the limit and goes to infinity, I switch the function. When I switch the function, this is no longer necessarily a good approximation for another f sub n. That's really what's happening. Make sense? You think about it. Yes. All right, so next question. Three. So recall Cantor function. So the Cantor function is g from the Cantor set to 0, 1, and it's given by g of y, which is g of k equal 1 to infinity of 2 ak over 3k. And what the Cantor function is doing, so in other words, it picks an element of the Cantor set. It figures out how to write this element as a sequence of zeros and twos, mod 3, right? And it creates out of it and here we have, of course, that ak is 0 or 1. And now I can take this function and I can create f. So let f be a function from 0, 1 to, I can say it's to 0, 1 still. Given by, so f of x is the supremum. So you remember the Cantor function is increasing, so this is the supremum over all y less than or equal to x of g of y. True or false? F is of bounded variation. True or false?
Sorry, Professor, it's 2ak over 3 to the k.
Yes, 2ak over 3 to the k. Sorry?
Where's y?
Where is y?
Yeah.
Y is here. For any y, you need to find the representation. So if you remember the Cantor set, any element in the Cantor set can be written as an infinite series of that form. So and this is unique. So this is the representation of y. So y is equal to it. That's y. So that's, I don't remember, is it chapter 2 or chapter 1 in Carothers, right? So there is a lengthy discussion of that. I reviewed it a little bit. So, true or false?
The Cantor function increasing,
Yeah.
so it'd be true because its variation is 1.
Brilliant, right? So it's a scarecrow question, just there's many symbols, but really, if you know the Cantor function is increasing, right, the variation is just take the top point minus the bottom point, right? It just moves up. The particle is moving up in a complicated way, moves up, stops, moves up, stops, moves up, stops. Right? Many times it stops, but you just count how much distance it traveled, right? Total variation is total distance traveled by a particle in a straight line, with the assumption that the particle is allowed to teleport from time to time. Right? So the particle, so it skips a distance, then it, teleported distance, is it considered as part of the variation, by the way?
Yes.
So yes, it is. Yes. So no matter how you move, you measure the total distance you traveled. Weird. In one, yeah. So answer. This is true. F is increasing. So what? So the variation from 0 to 1 of f is in fact f of 1 minus f of 0. F of 0 is 0. So this is just f of 1, which is 1. Wonderful. So four. So suppose that I have a function, and this means the set of discontinuities. So this is uncountable. F may be in bounded variation over AB. So we have a function that is that has many discontinuities, uncountably many discontinuities. Could it happen? Could this function be of bounded variation?
Yes, it's being increasing.
And if it's increasing, how many discontinuities will it have?
Absolutely many.
Yeah, we proved it some time ago, right? So what do you think?
Oh, then it can't, because it has to keep increasing and decreasing on some.
Not clear from what you're saying. Increasing, decreasing, sure, but
But it has to be doing that uncountably.
I mean, maybe it's just the particle is just uses a lot of teleporting, right? That's what happens. Right? Just jumps around, right? So could it be of bounded variation? No? Why not?
So jump infinitely many times.
And if it were countably many times, then it could converge.
Yeah, I guess we're wrong.
No, I didn't say you're wrong or not, but you didn't give me a reason.
It's kind of like that example, just like because you're bouncing too many times.
But how do you know you're bouncing too many times? I mean, bouncing many times, it matters also how much distance you bounce, right?
Yes.
Yeah, but
that is like really small, right?
all right, ready? I guess, right? So the answer is, what do you think? No, right? False. But the reason is actually simple once you know a good representation for functions about the variation. And the reason I asked is you should remember that if f belongs to the set of bounded variation, the space of bounded variation AB, f is equal to some h minus k, where h and k are increasing. Thus, right? So this representation is pretty clever, right? In terms of increasing functions. Thus, the total. So the discontinuities is just the discontinuities of h minus k, which is contained in the set of discontinuities of h union the set of discontinuities of k, and this is countable. Okay. So this is just to remind you that a lot is known about them. They're always the difference of two increasing functions. Let's try to then reverse this, right? So what happens if I say 5? Now I'm going to say if the f is countable, does it mean
Quick question before we continue. What does it look like when a function has uncountably many discontinuities? Because if, I guess I need to see an example outside of R, because in R, between any two discontinuities would be rational numbers that have to be counted.
No, that's not true. Discontinuities can be numerous. How a function of so think about the characteristic function of Q, for example, right? Its set of discontinuities is everything. It's basically how to see it. I mean, it means that what this function is doing to a single segment of, let's say, one-dimensional space. It basically just breaks it into tiny pieces and rearranges them. Right? So it cuts those pieces just and rearranges them somehow. Right? So for example, what is the characteristic function of Q is doing? It's taking the real number line, it's breaking it into dust, and it takes some of the molecules and recreates the number line. And takes the remaining molecules and makes another copy of something that looks like the same number line. You would not notice under a microscope that there are two different lines. So that they're not lines, in fact, right? They look like lines because the atoms have no length. So as you zoom in, you don't see them really. Okay. What about this? So suppose I found that my function has countably many discontinuities. Is it of bounded variation?
No?
And notice on closed ABs. So no, why not?
We had an example earlier where there were no discontinuities and it didn't have bounded variation.
Well, the limit did not, but each particular function had bounded variation. All right. So the limit of them, basically, you have more jumps. Right?
Then the tangent function would be
the tangent function. That's good. Yeah, I agree with you. Very good. So tangent function is a good example.
Could you just have an unbounded function in this interval with still countably many discontinuities?
Right. Yeah. Actually, dangerous thing, and actually, I have to discard the tangent function because tangent function is not defined on a compact set. Sorry, right? I thought, well, it's a nice example, but that's if it's open. But notice I require it to be compact. On a compact set, if it's continuous, it has to have both max and min. Right? That's my example as well, right? But it's not continuous. You can actually, if you fudge it a little bit, you can make a function, just make it jump, so that it basically it oscillates closer to 0, but creates.
That's 0 at the endpoint.
All right, so you can create a function that is basically doing this, right? Right. So that would make it continuous. So even if this is empty, it doesn't have to be of bounded variation. So answer is no or false. False. Take f of x to be sine of 1 over x. And here x is bigger than 0, less than or equal to 1. And 0 if x is equal to 0. So I didn't bother giving you a continuous function. But the set of discontinuities of f is just 1 point. Yet f is not of bounded variation. So what is it? 6. If f belongs to the set of bounded variation is continuous. Then f can be written as a difference of two increasing continuous functions.
How is this different from what we proved before?
Maybe it's not. I mean, what did we prove before?
So you can write the function as a difference of two increasing.
Yeah, but now I want it also to be not just increasing, but continuous.
It specifically shows the difference of like the arc length function and itself minus, like using the arc length function, wouldn't that be continuous function?
I'm not sure I know what you mean.
You'd find like a v of x equals the integral from a to x.
Well, not the integral, the variation from a to x,
Right.
right?
Variation.
Right. It can be an integral, but actually I avoided talking about an integral. We haven't yet.
That's true, yeah.
Yeah. But in fact, if you kind of know the redefinition of an integral, you can see that it should be one.
Well, is that function continuous?
The function v,
Yeah.
we actually showed something about the continuity of v, which is what you need to know, right? This function v does not have to be continuous, actually. Right? We know that that's Jordan's theorem. Jordan says that take a function of bounded variation, then it's equal to v minus f. Right? Both v and v minus f are increasing functions. But v does not have to be a continuous function. So?
True.
True. Why? True, false, why?
Because if it has a bounded variation, it can be written as the difference between two increasing function, and since f is continuous, I don't think you can write a continuous as difference between two uncontinuous functions.
Well, you
Yeah,
could
you
if
can.
the discontinuities,
Sure you could.
the discontinuities cancel each other out.
That's true.
No, in general, sure you can write a continuous function as a difference of two increasing functions. Plenty of examples of that. Take two increasing functions. Here is one subtracted. It's decreasing now, right? So just add them together. It's a graph that is somewhere between. Right? So if you have a curve like this, a curve like this, the difference is going to be some curve between.
Yes, but both of the function has to be
Continuous, sure.
Yes, that's what I mean. You cannot write down as a two discontinuous function.
All right. So the answer is actually true. And here's just one thing that you want to recall. We proved last time if, or basically I even wrote it down. V is continuous at x, and that's the interesting part. It's continuous if and only if f is continuous at x. Okay? So if f is continuous, so are v and v minus f. That's it, right? All right. So all right. So now new ideas. So given a function in the space of bounded variations, and where v of x is defined to be from a to x, define positive variation by p of x is 1/2 dx plus f of x minus f of a, and negative variation by an x equal to 1/2 ex minus f of x plus f of a. So negative variation, you see, we have f of x minus f of a. In the negative variation, we subtract it. In the positive variation, we add it. Okay? So what we can observe about it is that clearly v of x, notice there is a 1/2. So if I take this and add to that, I will get equality. So px plus nx. So negative variation plus positive variation is total variation until x. And we have also a representation of f here that is pretty nice. And that is that f of x equals to p of x minus n of x plus f of a. So we have proposition here. Let f belong to the space of bounded variations, and let v, p, and n be defined as above. Then we know that p is less than v and bigger than 0, and n is also positive. Two, p and n are increasing. They're increasing functions on AB. Three, if G and H are increasing on AB such that F is equal to G minus H, then the total variation from X to Y of P will be smaller than the total variation from X to Y of G. And the total variation from X to Y of N is less than or equal to the total variation from X to Y of H. So in this sense, N, so you remember that F does not have a unique decomposition into two increasing functions. But with the positive variation and negative variation, you have uniqueness in the sense of 3. Right? So for any other decomposition, the variations of each, P and N, are smaller than the variations of the increasing functions. So in that sense, that makes it a unique representation. So roughly speaking, what's the variation of increasing functions? You can just predict what it is. It's just like this, right? The steeper those, if I just approximate the increasing function by just a straight line, in essence, it's just like, right? So the steeper is this, basically what we have is, we have the function can be written like this or like this, right? I just vary the two increasing functions. This is the function g, and this is the function h. The graph is somewhere in between. Does it make sense? So you see what I mean? I'm just if I increase this a little bit, I have to compensate to produce the same f by making this steeper, right? So if I make g steeper, I must make h steeper as well. So p and n are the least steep functions. So proof. So you can observe the following thing. So total variation Vx is bigger than or equal to f of x minus f of a, which is bigger than or equal to plus minus f of x minus f of a. Thus, p of x, which is v of x plus this thing, is bigger than 0, and n of x, which is v of x minus that thing, is also bigger than 0. So they are positive since we have that v of x is equal to, by those equations, is equal to p of x plus n of x. We have v of x bigger than or equal to p of x. Because I drop this term, it's non-negative, I just decrease it, right? And v of x bigger than n of x. So let's prove now too. So how do we know that they are increasing functions? Well, what we can do is we can just do a calculation. Let y be bigger than x. Then we have that p of y minus p of x. That would be simply 1/2 v of y minus v of x plus f of y minus f of x, which is 1/2 of the variation from x to y of f plus f of y minus f of x. And this is bigger than or equal, this variation is bigger than just f of y minus f of x. This is bigger than or equal to 0. So this is just basically by a calculation, right? If you have this function, take p of y, p of x. So the reasoning for ny minus nx is similar. So actually, property number 3, Carothers leaves as an exercise. It's not a very easy exercise, so I'll show you. I think maybe it actually will be easy for you, but I had to think about it today in the morning. So observe that py plus ny minus px plus nx. So the first thing in the square brackets is just the variation of y. Minus variation of x. So this is variation of y, this is variation of x. Now this is equal to the variation from x to y of f. Now we have by 3 that g and h are the two increasing functions that represent f. So this is the variation of from x to y of g minus h. And by triangle inequality, this is less than variation of g plus variation of h. Okay. Now, because those functions are increasing, because g and h are increasing, this is just g of y minus g of x plus h of y minus h of x. So what did we observe? Thus, if we rearrange those terms, we have that py minus px plus ny minus nx is, well, first of all, what is that equal to? This equals to, p is an increasing function, so this equals to the variation from x to y of p plus the variation from x to y of n. And this, we observe, is less than or equal to variation vxyg plus vxyh. Let's place this as 1. Now, so give me 2 minutes, right? Just 2 minutes and I'm done. Okay. If you have to run, run. But I think in 2 minutes I will have it. Now, what we have a representation for f. So f, remember, is p minus n plus f of a. And f is also g minus h. It has those two representations. Thus, if I take f of y minus f of x, what I will get is this expression at y minus this expression at x. So I'll get p of y minus p of x minus n of y minus n of x. And this is simply equal to variation from x to y, because p is an increasing function, variation from x to y of p minus the variation from x to y of n. And doing the same thing for g minus h, we get that this is going to be equal to the variation x, y, g minus the variation x, y, h. Okay? And this is equation 2. So we have inequality 1 and equality 2. So then if you do adding 1 plus 2 implies, so if you add this equality to the inequality, it implies that the variation from x to y of p is less than or equal to the variation from x to y of g. And subtracting, so that would be 1 minus 2. That will imply that variation from x to y of n is less than or equal to variation from x to y of h. And we are done. Okay. So when you think about those things, when you review it, try to write it without looking into the notes. All right. Have a good one, guys.